All right, everybody, welcome to the Go for Guides free testing and benchmarking workshop today. My name is Cory LaNou, and I'm going to be your instructor for today. So we have a lot of information to go over. We've got about an hour, which I think we should be able to get through most of this. We're going to go ahead and start with the testing first. Testing, let's go ahead and jump right in here. It's about 5 after, so we've got time to get started. So testing in Go is actually really easy. There's a really strong emphasis on testing in Go. The compiler is going to catch a lot of bugs for you because, as we all know, Go is a statically compiled language, but that's not going to do anything about ensuring that our business logic is sound or bug-free. So we all know that we should be testing, especially to prevent regressions in the future. And in Go, there is some convention that you have to follow, naming being the big part of it. And this is, I think, where people get a little confused the first time they start testing in Go. But it's really important that you follow the conventions. So one of the conventions in Go to actually create your test is you actually have to have the file name named properly. So if you've got a foo.go file where all your code lives and then you want to go ahead and write a test for that file, the convention is to basically call it the same file name and then give it an underscore test.go. Now it's very important that you do the underscore test.go. If you do not, the test framework will not pick this up. So this is really important. See where I'm highlighting right here, the test.go? Very important that we have that. Okay, so like I just said, we have to make sure that we actually have this underscore test.go. This is required naming pattern by Go. If you don't do this, it's not going to run the test that you think it's going to run. The other part of this is after we have this test file, so this is the test, the content of that test file right here, we also have to have another naming convention for all of our actual tests. So right here is the actual name of a test. It's just called test simple. It really doesn't do anything. The important part here is this, all of your tests have to start with the word test with an uppercase T. If you don't start with this, it actually won't run the test because this is just code. And it's very common in your Go files and your test files to have all kinds of helper code and things like that as well. So you can create different functions and methods and full structs and the whole works in your Go files, test files. And if you don't call them underscore test, they won't be run, but you can use them as helper methods inside your test. So the convention for Go is if it sees an underscore test.go file, and then it sees any function that starts with the word test uppercase T, that's how it knows how to run the test. Now, I cover this a lot of times when I do the training, and even after I cover how important it is to get this naming correct, I always have people come back to me and say, hey, my tests aren't running. So again, it's super important. Underscore test.go is the name of the file, and all of your tests need to start with the test word with the uppercase T. So notice that we actually pass into all of our tests this argument right here, T, and then it's a pointer to testing.t inside of the package. Basically, this is the harness that Go gives us to kind of do all of our testing and gives us all the methods. And so these are a lot of the really common methods available basically to control the flow of a test in Go. So things like error, failing, fatal, log, skipping. There's a bunch of other ones we'll go over as well, but these are the common ones that you'll end up using quite a bit when you're writing tests in Go. So the first thing I want to really talk about is formatting test output in Go. This is really important, especially if you're working on a team, and I'm kind of a stickler for this when I write tests and output, because I like to have very valuable output in my tests and very meaningful output. So we'll go over this basic test right here. So if I have this basic test and it's add 10, and basically ignore all what it's doing right here, but at the end of the day, we just have this t.fatal unexpected value. So if I go ahead and I run this test right now, the output that I'm going to get is I'm going to get, oh, this test failed. Okay, so I know the test, and it's test add 10, it failed. It's on this line right here, and the failure is unexpected value. Now, the reason that I really don't like this output right here is that this output doesn't tell me much about what actually failed in the test. It just tells me it had an unexpected value. So now me, as the person who just changed some code probably in the application somewhere, I get this new failed test, and I really don't know why it failed. I have to go and I have to chase down this file right here and go to that line. It's a little bit extra work for me. And I'm a lazy developer by nature, so I don't like to do extra work. So here's a little bit better. So this one right here, we're going to basically do a t.fatal. And we're basically going to say, hey, we got an unexpected value. However, we got this value right here. Now you'll see that the output here is a little bit better, right? So we've got unexpected value, and it says that we got 12. So this is better for me. I can look at this output and go, okay, looks like this test failed. I got an unexpected value, and I got the value 12. Well, I don't really know what the value was that I was supposed to get. So once again, I've got to chase down this line of code and go check it out. So an even better output, and this is kind of the preferred way that you'll see a lot of tests written in Go, is we'll basically say what our error was, and then we'll say what we got and what we expected. And so now when you look at your output, you're actually going to get this really nice format. It's going to say unexpected value. I expected 11, but I got 12. This a lot of times is enough information for the person actually writing the code that just created the test failure that allows them to not even open up the test and go ahead and actually just fix it on the fly. So I prefer this type of output, and this is the very common convention that you're going to see in a lot of the actual Go testing out there. So try to always follow this format. I do have one more format that I like a little bit better, and this could be referred to as maybe gold plating your tests, but this is my preferred method. If you're used to writing Go, you're probably used to seeing this where we basically up here can declare a couple of variables and it equals these right here and it instantiates it. So basically I'm going to set got equal to the actual method, and I'm going to set expected equal to this actual constant 11 because that's part of my test. Then I can simply say got does not equal expected, and then it's really easy when I format this string as well because got is going to correspond to this got and expected is going to correspond to this expected. Now you'll notice that we don't change the output of the actual failed test, right? This is the exact same output that we had on the last one, but the difference is here, let's say that we actually update our method and it has a different expected outcome now. All we have to do is just change this one value right here, and I know it's a subtle change, but if we go back to the other one, notice we would have had to change 11 here and then change 11 here. And so in this new format, if we do it this way, all we have to do is change 11 this one time, and all of our format strings are still going to work out. All of our comparisons are still going to work out, and we're still going to get the same exact expressive output of the actual test output. So again, this is my preferred method. Not everybody agrees with me on this. I think some people think this is gold plating, and that's fine. But just something for food for thought. If you like it, go ahead and do that. If not, that's fine too. But at bare minimum, this is kind of the bare minimum you should be trying to do for your test. The bare minimum is get the expected and the got. That's pretty important. So you might hear a lot about table-driven tests in Go. In other languages, if you've worked with Rails or some of those other frameworks, they basically have set up and tear down functions that can be run before and after each test. Go doesn't really have that built in, so we end up doing that basically because we have table-driven tests. And so we'll create a bunch of setup and tear down around these table-driven tests, and that works pretty well for us in general in Go. And so if you're wondering what a table-driven test is, we'll kind of go over that. So in Go, it's very common, and this is a format that you're going to see quite a bit for table-driven tests. We basically just create this anonymous struct right here, and we're going to assign it to the value TT, and it's a struct, and these can be any values that you want. In this case, I just have A and B, which are two ints, and then I have expected, which is the actual result I'm going to get. I'm going to go ahead and I'm going to initialize all these values right here. So A to 1, B to 1, expected 2, and so on and so forth. So these are the tests that I'm going to run. So there's actually 4 different tests in this table-driven test. Then I just have a basic for loop that I'm going to range through these tests, and I'm going to just create the got variable. I'm going to say x.a plus x.b equals got. And then I do my test assertion right here. If got does not equal expected, I go ahead and fail. Now, I purposely created some failures in this test just to see how this table-driven test works. And you can see now it will go ahead and loop through all of these tests and run them. What's really nice about table-driven tests, it allows you to very quickly add a lot of different scenarios and easily look at them and reference them and run all your tests. So this is something that's very common in Go. We use this quite a bit. And it can be anything. I like to also add maybe a name up here as a variable so I can actually have the name of the test, so on and so forth. But again, very basic table-driven test right here. And what's nice about it then, if you just want to add another test, you just basically add one more line here and you can add more tests. Very, very nice. However, one of the shortcomings with a table-driven test is the fact that when it does fail, it's very difficult to isolate that single test in the loop. And so I've seen already where we have, in some projects I've worked on, very large table-driven tests, sometimes hundreds of different test cases. And out of those hundreds of test cases, you only have one single test that's failing. And with the way that table-driven test is written there, it's very difficult to isolate down to just that one test. You have to keep running the entire test suite, and that's very frustrating. And so in Go 1.7, they actually added the ability to run subtests. Now, this was a really fantastic addition. I use it quite a bit. You'll see that from a table-driven test standpoint, it's almost identical. So this setup right here, the struct, is exactly the same that it was before. There's no difference here at all. We've got the same for loop for the most part. And the only difference now is that we actually have a t.run. So this t.run will actually run a subtest, which is really nice. And so this t.run, I basically want to give it a subtest name. It takes the first argument is the name of the test. and then it takes the actual function for testing. And so now I can go ahead and it's the same test here. And the only difference is now I want to reference this st for subtest variable, which is what I passed in right here. This is pretty much the same as what you had before. If I go back here, you'll see it's very similar. However, we've got the subtest. You might be asking yourself, okay, what did I really gain here? Well, if we actually look at the actual output now, we'll see that this failed the actual subtest itself, but now it fails each line individually. And so it's the same line of code, but we see it's subtest number 3, subtest number 2. And what that was is because up here we actually passed in the index of the actual test we were passing. So that's a very simple way now we can actually isolate this out. And then I can actually show you later on when we run these tests, if I want to isolate just to this very simple test, using the -run parameter, I can actually give it that exact test itself. And now I can run just this single subtest in the entire table-driven test. I can isolate it right out. So it's very, very nice. You might have noticed, if you haven't already, that in the test, we actually have what we consider a magic testing package. So I think a lot of you already know that you can only have one package name per directory. So if you have a directory and it has a package foo in it, we can't have any other files in that directory that declare a different package, except for if it's _test. So this is kind of a special magic testing package that Go lets us create. And that allows us to effectively do what we call black box testing. So if we declare in the test the actual package name we're already using, this is what we're going to consider being an internal test, which allows us to actually access all of the local private variables or the local variables and so on and so forth in that package. Now, typically that's not that desirable. We do like to do black box testing because it actually really helps you test your API. And so we try to do as much black box testing as we can. I think you've got people that will say that you always have to do black box testing and there's no other way to do it. I don't subscribe to that. I do have internal tests from time to time when it's necessary. However, I do try to do as much black box testing as I can. So to create a black box test, all you have to do is take the same package name that you had before and add the _test to it. What this will do now is it will basically create an external package that you're testing from. Since this is technically a new package, all the rules around exporting in names, public, private, are also in effect. So if I have a foo.go, I cannot access from my test this variable here because it's lowercase, it's not exported. However, I can access this variable b right here because it is exported. Okay? Again, this is really important. It's really helping you test your abstraction and your API. So again, as much as possible, I would suggest trying to do the black box testing. So running tests. So now that we've actually got our tests already created, you can go to the command line. You can actually just run this right here. So if you just run go test dot, that will actually run the tests that are in that current directory, the current folder that you're in. If you want to run all of the sub packages in Go from the top level of where you're at, you can run go test dot / dot dot dot. Now, I'm not sure where the 3 dots come from. That's something I had to get used to, but just take special notice. That's not 2 dots there, that's 3 dots. And what that will do is that will actually go recursively through all of the subfolders at this point from where you're running this and run all of the tests. So this is really nice if you just want to run all the test suites very quickly and Go. We can also use the -v. I typically use the -v, especially if I've got this in the CI environment so that I can see all the verbose output rendered to the logs. And so this will actually go ahead and run all the tests, and it will say each test that it's running, how long that it took, and if it passed, and give me all the outputs. So this is one of these cases where if you want to see everything that got output and just ensure that everything's running properly, -v is really handy. The other one that I really like too is this testing verbose. So a lot of times if you're working in a larger application, you've got a lot of logs that are going all the time, and that can be very confusing and very difficult to kind of sort through if you have a test failure. So a lot of times what I will do is I will check the testing verbose file, and if verbose is not on, I will actually silence the actual loggers in the actual application itself. And what's really handy about that then is if I'm running a really long test and it's really complicated, it gets rid of all the noise for me very quickly. And so I really enjoy that quite a bit. And so to do that, you simply just do if testing.verbose, this is just a test right here, then you can do whatever you want, right? So maybe we want to log some extra information about it. But more than anything, what I'm really looking to do is I'm looking to silence my logger. So a little trick you can do if you're using the standard library logger is you can just literally set the output to io-util.discard, and that will silence all of your loggers now. And so then none of that output's going to come out into your test screen. And so then you'll only see the output from your test, which is really handy and it can be very nice to do. So again, this is just depending on the test and the application, but this is a trick that I learned a while ago, and I do use it quite a bit in some of my larger applications. Another one that I really make use of a lot is the short flag. And so by default, this is off. You have to actually turn it on when you pass -short to the actual test when you run it. So you can see right here, if I say go test -v, which is verbose, and then -short, this will turn the short flag on. This is really handy when you've got a larger application. Maybe you've got some long-running tests. Maybe you've got some integration tests that require external dependencies, such as a database or some type of messaging service, so on and so forth. And a lot of times when you're just doing a lot of local development, you don't care about these longer integration tests. You want a shorter cycle to kind of give you the information back very quickly on whether or not your tests are passing and the code that you're changing is working. You don't necessarily require the integration test to do that. So if you do go ahead, what my idiom here is I typically look and see if testing.short is turned on. And if it is, I just skip the test. And I just go ahead and I put this t.skip in there. And I basically put a message out that says, I'm skipping this test because I detected short testing is detected. And this is really nice because now I can see in my output that this test wasn't run because I passed in short, which is what I would expect. But now my tests run really fast. Otherwise, if the short flag is not turned on, I can go ahead and just either log this out or just let the test run. So this is something that I highly recommend if you have integration tests or long-running tests and you want to run your local test suites a lot faster for just a lot quicker feedback cycle when you're developing. This is a really handy way to do that. And so I use this quite a bit anytime I have, especially integration tests that require external dependencies. Another one that's really nice, if you've written your test so that they're not stepping on the other tests when they run, you can put the t.parallel in there. This will speed up your test suite quite a bit because it allows any test that's in the test suite that has this flag turned on, it will run all those tests in parallel. So as you can imagine with Go, the more tests that you have in parallel running, the faster your test suite's going to run. So by default, I pretty much turn t.parallel on all the time in my tests, unless I know specifically it's a test that's maybe an integration test that has to access the database and things like that, where then I want to make sure the isolated data is intact. But for the most part, most of my tests, I don't have to do that. And so if I turn on t.parallel, that's going to make all my tests run a lot faster. So in general, if you're writing your test suite from scratch, I highly recommend to always turn on the t.parallel. If you start having problems with data integrity because you're stepping across boundaries and it's not an isolated test, then obviously you have to turn that off. But for the most part, this works out pretty well. So remember I talked earlier how we can actually run specific tests. And so this is one of those things where you can pass the -run flag in, and then it just takes a regular expression. So if I pass in and I've got a bunch of different tests I want to run, and I want to run any test that's got the word call in it, I can go ahead and pass in this. It's a real simple regular expression. It's just going to match the actual word. It will run all the tests in my test suite that match call, which is really nice. And so this is really important then to think about when you're naming all of your tests. What I try to do is I try to name all of my tests logically around a certain method or certain function or even a certain grouping. This allows me to test a very specific set of my code quickly because I've named all my tests such that if I pass in a regular expression, I can match an entire group of tests at once. So again, this speeds up my feedback quite a bit because now I'm only testing the handful of tests I care about in a large test suite. So I make heavy use of as well of this -run flag. Timeout's also really important. A lot of times you'll have maybe a deadlock condition if you're writing concurrent code or things are just taking a lot longer than you want them to. And so typically I pass in like a default timeout 10, 20, 30 seconds, whatever is appropriate for the code that you're testing. And then if it exceeds that time, it's actually going to go and basically effectively panic the code. And it's going to get a sig quit output, which is going to give you the entire stack trace of where everything was happening. Especially if you're doing concurrent testing, you end up with a deadlock. This is really nice because you'll see all the Go routines that we're running and kind of help you track down which Go routines were blocked or where my block actually happened in your test. So I almost always run everything with a timeout, and that's pretty important, especially for deadlocks. If for any reason you notice that your test just isn't coming back and you didn't pass the timeout flag into it, you can actually use the, on the Mac or Linux, you can do Control + /, or you can actually kill it with a sig quit. I'm not sure what it is on Windows. I keep needing to look that up. But on Mac and Linux, it's an easy way to basically kill the Go binary, and then that will go ahead and give you the stack trace that you're looking for. Code coverage is also another really important part of testing. Go actually ships with this out of the box, which is really nice. And so code coverage is really pretty simple to do. All you do is basically just do go test -cover profile and give it the output of the file you want. And then you can run the next one, which is go tool cover. and you want to basically say I want HTML output, and then I pass in the coverage file that I just generated ahead of time. And then you can open up this this will actually open up the browser that's set on your system, and it will give you a nice look like this. It's going to give you the not tracked, the not covered, the covered. This will be a drop down of the different files that you want to see. And then anything in green is effectively the code that you've effectively covered. I have a question here. Is there a special flag to enable disable parallel on the Go test command line? There is not on a per test, but you can disable it per folder or package. So by default, all of your packages run in parallel, but you can disable that. And if you look at this Go test help, I believe the proper one for that, does it say in here? I'm just looking for the help on this. Can't remember what it actually is. I thought it was parallel, but I don't remember specifically. There it is right there. So you can use the dash parallel flag right here, which is allow parallel execution of test functions. Oh, actually it is t.parallel. I thought there was one for the actual test packages as well. Yes, the dash P will actually change whether or not all of the packages will run in parallel as well. So dash parallel is for t.parallel inside your test, and then dash P itself is for the actual package test. So there's two different ways you can disable and enable the parallel testing. So if I want to run specific code coverage for just a very specific test, I can also run the same thing I had before. I can now, again, still use my dash run. So if I want to see just the code coverage a specific test is giving me, this is really handy as well. And this is how I do a lot of my testing. So when I'm running my tests, I narrow down my code coverage to the test that I'm running because I want to see the code coverage and kind of see where the actual code's hitting to ensure that my test is doing the exact things that I think it's doing. Now, this is only good for while you're developing the test, because when you run the entire test suite, you're going to see code coverage across the whole thing. But this does really help me think about what I'm testing and if I'm testing the way that I expected to be testing. So I use this little method here quite a bit and effectively just only cover the tests that I want to actually see the code coverage for. Very, very fine detailed. I know a lot of people don't do that, but I'm kind of meticulous that way. I don't really have an extra time for the setup because all my test suites run automated, which I can show you at the end. And this is something that I've found to be a really good practice on my end because it's helped me catch a lot of bugs that I probably wouldn't have caught just by running the test without watching the code coverage being generated at the same time. Now, I don't know if you've ever used GoConveyer, but GoConveyer is just a fantastic little tool that does a lot of this automation for you. It does have a lot of test suite stuff you can use in addition to this, but for the most part, if you just want to use it right out of the box, it doesn't require any additional changes to your code whatsoever. You can just do go get and go ahead and get the GoConveyor, and then from your project root, just run the binary GoConveyor. What that will do is that will actually spin up this page right here, which I'll come to in a minute. But GoConveyor actually does quite a few things. It directly integrates with all the Go tests. It's a fully automatic web UI. It does all the huge suite of the regression test. It shows the test coverage as a Go 1.2, which I'm pretty sure everybody should be on by now. It's readable in colorized console, which is super nice. It does have test code generators, desktop notifications, which are actually pretty nice if you just want to run it in the background. And it actually supports different editors as well. So this is effectively what you get, which is really, really cool. This over here on the left side is basically all your different packages, and it kind of gives you kind of a little bar chart on like how much coverage you have. As you have less coverage, it'll actually go yellow and then red, which is pretty cool. It kind of shames you in a little bit to actually writing some tests. And then here's the actual output. And then you can just click into any of these as it's going and actually see the actual test coverage per file. So super, super handy. The next thing we'll get into is race conditions. So if you're writing concurrent code, race conditions are really important. Go is pretty nice. They actually ship with a race detector out of the box. Now, a race condition, to be very specific, is effectively anywhere two or more Go routines are accessing the same piece of memory and reading and writing at the same time. And while that may not create a crash in your program, it will if it accesses a map concurrently, but if it accesses other parts of memory, such as a struct, it won't crash. However, you now are going to have a program that doesn't have predictable outcome because you may be reading dirty data, etc. So you really don't want any race conditions in your concurrent code, and Go makes it really easy to kind of enable a race detector and hopefully to try to narrow some of those areas down. So if we just looked at a very simple piece of code, we're just going to go ahead and increment this variable that we've got there. And we're going to go ahead and run some Go routines. And if I expand this code out right here real quick, you'll kind of see that I've just got this. I'm going to run some Go routines, and I'm just going to go ahead and keep incrementing these and accessing the same space. This is going to basically create a race condition, and I'm doing that on purpose. Really bad piece of code, but I need to simulate the race condition. If I go ahead and just run the Go test, race test, notice how it doesn't fail. It's going to go ahead and tell me, hey, everything's fine, your test's fine, exactly what we expect it to be. So that's pretty cool, and you would just think that's fantastic. However, if I add the dash race to it, which is where is the, right here. If I add the dash race to it right here, and then I run the race test.go, it's actually going to tell me there's a data race. In fact, what this is showing you right here, if I was actually to run the code may actually panic at runtime. And it's going to give me this error. And so now my code's actually going to break. So even though my test passed, my code's actually going to blow up in production, which I really don't want. So if I pass the dash race flag when I do my test, and this is something I typically do in the continual integration stage, it's actually going to tell me that it detected a data race. What's really nice about this, if I actually read through it, it's going to tell me that this is the line right here that it actually saw the read happen at, and this is the line that it actually saw the actual write happen at. So I can actually open the code right up and go exactly to where the reads and the writes actually happen. Now, in production code, it's usually not as simple as just seeing that. You have to go up the stack a little bit to actually find out what was calling what and how that ended up being a race condition. But the super nice part is that the race detector definitely gave you the spot to start looking in. I use this a lot. It works out really, really well. I typically enable this for anything that I'm doing the continual integration for. So as this slide is basically saying right here, I always have this set in my CI environment, always, so that I don't always run it locally because it does make the test slower, but there's no reason not to have it always engaged on your CI. And the other thing about the race detector, it does make one promise. If it does find a race, it's a race. And it only finds a race by seeing that memory being accessed at that time when you're running it. So if your test doesn't simulate that race, it can't find the race. However, so it doesn't guarantee it's going to find all the race conditions, but it does guarantee that if it finds a race, it is a race. Don't argue with it. I've done that before. You're going to find out that you're wrong. It's definitely one of those things where it finds a race, it is a race condition. I also have some lightweight automation that I use. I use a tool called Reflex. It's a really handy tool. The link is right on here as well. And this is just something that was basically, it's a file watcher. It works out fantastic. And what I do is I basically tell it that, like if I want coverage to run, I just run this command Reflex and I tell it to run this shell file. And inside the actual coverage itself is just basically creating a cover profile. It's going to create the Go tool cover, and then it's going to tell me that it was created. What I additionally do is I actually open up this file right here in my browser, and I have live reload hooked into it on top of it. So I actually have a browser that's open. I'm watching code coverage get basically filled in live as I'm writing my test. So it's a pretty handy thing that I use quite a bit. I really do enjoy this a lot. Again, it's probably overkill for some people, but like I said before, I'm very meticulous when I write my tests, and I like to see the code coverage actually fill in as I go, and it really does help me write my tests a little bit better and think about them in ways that I might not think about if I didn't see them actually doing the coverage at the same time. Another thing you can do as well, if you want your test to run a lot faster, is you can actually turn off the garbage collector. So you can set the Go garbage collector environment variable to off just for that specific test. So if you put this in front of running the test, it'll actually turn the garbage compiler off, and it actually runs your test a lot faster. This may not be optimal for everything, but I use it quite a bit. It used to be a lot bigger deal before the garbage collector got much faster. I don't do it as much anymore because the garbage collector is doing a fantastic job nowadays, but this will speed up your test a little bit. So if you want to do that, just a little tip right there. You can turn that off while you run your test. Don't do that for benchmarking because it's certainly going to skew the way your benchmarks come out, so you would not want to do that. But for just basic testing, that does work out kind of nice. So we do have some exercises right here. We're not going to do them because we've got a workshop going on and we've got to kind of get through the next benchmarking part. But feel free to come back and actually do these exercises. Just basically write some basic tests and kind of give you an idea of which tests to write here if you want to actually create some. But we're going to go ahead and move right on into the actual benchmarking here. So benchmarking basically allows us to create a baseline measurement of how our code's performing. This is kind of the first step into profiling your code. It's not really profiling, it is benchmarking. It's really nice. I use a lot of micro benchmarks all the time. And the reason I use micro benchmarks is it kind of gives me an idea as when I go from one version of my code to the next as I'm making changes. Am I going up or down in performance. Now, getting better or worse doesn't necessarily mean bad. It just means it's changed. And so what I typically try to do is I try to look at if I see really big changes in my performance for better or worse, I might go and check and see what I actually did. I've actually had it where benchmarking something actually got really good. I watched a function, wow, like I increased performance by 1,000%. It actually was a bug, so it wasn't doing what I thought it was doing anymore. So just because you improve the performance of a benchmark actually doesn't mean that you didn't introduce a bug. I do have a question here. Someone's asking me, for table-driven test, when testing output like JSON, would you need to structure the response to what expected from the server? Yes, when you're testing JSON, it can be rather tedious. You actually have to create the entire JSON exactly how you would expect it. And I feel that it is important to take that step to do that because JSON is part of your contract that's going out to the API. And if it doesn't match exactly what your test has, even though it may be a little brittle because it's the exact JSON you're expecting, it should be brittle because if it does change, that means it's potentially changing your contract out to your end user. So I would definitely take the time to write out the JSON. You could write some helpers maybe to generate some of the JSON with you as well. It is just Go code, so if you want to write your own helpers for that, that's also very common. But fundamentally, you do have to create it so it has to know exactly what JSON it's going to do. All right, so back to benchmarking. Benchmarking effectively makes it possible to know what performs better, and there's not a lot of need for guessing. One of the things you hear me talk about Go all the time is people will talk about performance optimization, and I'll see some code come across for a pull request, and I'll look at it and I'll be kind of confused like why it's doing what it's doing. And when I'll ask the person, why is this code kind of extra complex? They're like, oh, well, this is going to perform better. And I always ask them, well, how do you know that? Well, it just will. And I always come back, especially in Go, I'm like, well, then you need to prove it to me because we have benchmarking and we have profiling. And if you can't prove it to me with those tools that Go already provides, then you're going to have to rewrite it and make it simple because one of the tenets of Go is running simple, readable code. And if you're making it obscure because you think it's going to run more performant, you're going to have to prove to me that through the tools you can do that. And with Go, there's no reason you can't prove it. So I always tell people you don't get to make anything and do any premature optimizations without being able to prove to me why you're optimizing it. So there are some ground rules for benchmarking if you want to get repeatable results. This is really important if you're doing higher end applications. And so I definitely recommend that you take these steps. I don't go this far for a lot of my small applications. I'm just trying to get a frame of reference for the most part. And so benchmarks can give you a frame of reference on your laptop. However, know that if you run a benchmark on your laptop, there are so many things that can affect that benchmark just from an actual hardware standpoint that it's almost impossible to get repeatable results. So, some of the things here we talk about is, obviously the machine has to be idle. We don't want to profile on shared hardware. You don't want to be browsing the web, going on YouTube, any of those kind of things. You also have to watch out for power saving and thermal scaling on laptops. So that's a big deal. Certainly avoid virtual machines or shared cloud hosting. They're way too noisy for consistent measurements. So don't think that you're going to just run some hardware on AWS and start using that for your actual repeatable results. That would be a disaster. There was a kernel bug in OS X versions less than El Capitan. So you want to upgrade to avoid the profiling bug on OS X as well. So effectively, if you really want to do benchmarking the right way, you're going to have to spend some money and get some dedicated hardware, bracket, and disable all the power management and thermal scaling. Never update the software on those machines ever because that'll change your benchmark results. So it's just one of those things where it's an awful lot to take in there for benchmarking ground rules. That's for typical pretty high-end applications, but it is important to understand that if you're working on higher-end applications. For most applications, if you're just trying to get some type of reference point, then obviously running it on your laptop, that's fine. But again, understand it's a reference point and not a repeatable result, and there's definitely a difference in those two concepts. So writing a benchmark is very similar to writing a test. And so here what we have is I just have this basic Fibonacci function right here, nothing really fancy. And again, there is a convention here. Notice how I have this function, and it's called benchmark fib. The important part here is it has to start with the word benchmark uppercase B. It takes a signature very similar to how the testing signature works. Instead of a testing T, I'm going to get a B for a testing B for benchmark. Now this part right here is really important. All of your tests, go ahead and have this for n colon equals 0, n is less than b dot n, n plus plus. So this is a really important piece right here to understand that this is part of the framework that you're going to get. And then you just call your actual method that you're testing right here. So what's really cool about this is the testing framework for benchmarking will actually figure out how many times it has to run this benchmark to get a measurable results. Because depending on what your actual benchmark, if it's a really small piece of code, it might have to run it 10,000 times or 100,000 times or even 1,000,000 times to get a measurable result for repeatability, to really understand like how long does this really take. However, you're running a bigger piece of code, it might only have to run it 100 times or 1,000 times. But that would be really tedious. You have to come in here and keep optimizing this loop to know how many times to run it. So the nice part about that is the benchmarking framework takes it out of your hands and actually does all of that for you behind the scenes. All right, so that's a basic benchmark. So if I want to run a benchmark, it's really as simple as just go test dash bench dot. Now what that's saying is it's running the test framework, but I'm saying dash bench equals, and dot means everything, right? It's just a regular expression at that point. So if I'm here and I see this is my one test right there, and I cap my fib test to show you that that's the test I'm going to run, and I run this right here, it will go ahead and actually just run that. Now, notice what it told me here is it ran this benchmark. It ran it 30,000 times, and it took about 44,000. It did 44,000 operations per nanosecond. So that was really moving quite along there, moving pretty fast. But it actually ran it 30,000 times. Now, notice that 30,000 times, that came from this loop right here. That's how it knew that. I did not have to tell it to run 30,000 times. It knew to run 30,000 times to get that measurable result. So again, very handy, does it on its own. A lot of times it's really nice to actually be able to compare benchmarks. And so if you want to run them more than once, you can do things like you can do the dash count 20. And so if I go ahead and I want to run 20 times, somebody's asking, weren't those 44,000 nanoseconds per operation? Oh, yes, I'm sorry, you're right. It ran 30,000 of these, and they were taking 43,000 nanoseconds per operation. I'm sorry, yes, you are correct. I should learn how to read my own output. Apologize for that. So here's one where if I want to run this more than once, I can give it the dash count 20. And what this will do now, it'll actually just keep running that benchmark over and over and over. So this is a way that if you're running on a laptop, this is a really good way to figure out, am I getting somewhat of a repeatable benchmark here? And when you notice that we're not fluctuating very much in between all these benchmarks, that gives me a pretty good feeling that, you know, even if thermoscaling or something was kicked in, at least I know that it's kicked in for all of it, and I'm not seeing massively wild fluctuations. It does give me a fairly confident reference point at that point. So if I go ahead and I improve my Fibonacci, I may go ahead. So before we had this right here, where I was basically running recursive calls. And then I have another one where I'm like, well, let's see if changing this right here, this Fibonacci, let's see if this actually makes it run better. So I've had this old function, and then I create a new one, right? So now I've created this new one. I want to benchmark it again. It's really hard to do all this benchmarking and do it by hand and kind of compare them. So there's actually a tool that Russ Cox actually wrote called BenchStat. Here's BenchStat. It's got a lot of different stuff in it, but effectively all we do is to get it, you just do the go get for BenchStat. And to use it's actually pretty straightforward. So all I do is you saw before, is I can actually record the old benchmark to a old.bench file, which is what I did here. So I can go ahead and do this to old bench. And then I can go ahead and run this new benchmark and tell it to go to new bench, and it will create that. And then for when I want to run the bench stat, all I do is pass in the old benchmark file and the new benchmark results. And it will actually go ahead and tell me that the old time was this, and it was about 11% different than this one. So it actually tells me that delta was about 99.97%, right? So it gives me an idea that I got a little bit better with the new one. I shaved off some time, so that was good. So it means that from the old one to the new one, I actually got faster. Not a lot, it's pretty marginal, but it means I got faster. So you could effectively write some automation around this to run your benchmarks and then feed them through BenchStat and then create a nice report for that. I thought somebody had done this at one point. I've searched and searched and searched, and I just have not found a nice tool that actually does this automated wise. If anybody does come across one, please let me know. I would love it to get better. Oh, somebody's saying it looks like it got a lot better. Yeah, you're right. It did get a lot better. It was about 0 microseconds. So it shaved off 99% of the time. Correct. So it got a lot faster. But yeah, if anybody finds a tool that actually allows me to run all my benchmarks from my old one to new one and then compares them, it'd be nice to actually pass on like just two different branches of the code. and tell it to run benchmarks on the old branch to the new branch, and then give me a nice report. So I keep asking people to write something like that for the community, but I don't have it yet. So I'll just keep asking, so hopefully somebody writes that, because I don't want to write it myself, but someday I might have to anyway. Because that would be a super cool tool, and it'd be super nice to have like on a CI or something like that, so that when your CI runs it, it can say, here's all the benchmarks now compared to what they were on master, and tell you if you got faster or slower. So the other thing that's really important is, especially for small benchmarks, you'll find that things actually do compiler optimization. So compiler optimization, as we know in Go, is a pretty smart compiler, and it figures a lot of things out for us and tries to make our code faster. Well, the problem with that sometimes is that it actually will do the same thing for our actual code in benchmarking. And so I can show you what I'm talking about here. So let's go back here to go to, let's see, optimization. Okay, so what do I got here? Subtest. Okay, so I've got this test right here that basically is going to it's going to benchmark the sum. And if I do go test dash bench, I run this test or this benchmark, you'll see that it ran it a lot, and it ran super, super fast. Now on the surface, I look at that and I say, wow, that's fantastic. This thing is running really, really, really fast. And I think everything's good. However, the problem with this is, you probably didn't realize, it actually ended up optimizing the code out. And what I mean by that is it realized that the code that was being run right here actually wasn't being looked at anywhere. Like, we weren't returning the results, right? And we weren't actually looking at the actual data that was doing. Even though we were calling this function right here, it knew that nothing was being done with the results of that. And so the compiler was smart to actually optimize that out. So what we effectively had as far as a benchmark at that point, we were running an empty benchmark. We optimized the code right out of there, and now we're running this empty benchmark, and we're actually not checking how fast this function actually is running. This is pretty common in really small methods, so you want to make sure that you are taking care that you don't have these accidentally optimized out. We can do that by basically tricking it. And we trick it by basically creating this global variable up here, which is going to force it to escape at this point in memory. And so now we have this var r int, and we can say r equals sum I, comma I, and then we can set the result of r at this point to this global variable. This is going to force it to keep track of this variable the entire time and set the result back out, which will make it so that we can no longer optimize this piece of code right now. It's kind of a funky little thing that you got to look at, and it looks kind of odd at the beginning. But it is really important that you do this for these smaller benchmarks to make sure they don't optimize out. So now you'll see if I ran the old benchmark, I was getting really small results. But when I run the new benchmark, I actually see that I get a little more results. Now, again, this is a really small function, so it's not a noticeable difference. But in a larger function, it would be much more noticeable in the time that you're running. So again, it's really important to make sure that when you're doing benchmarks, that you're not accidentally being optimized out. I've had that happen to me in the past, and I haven't caught it, and you think your benchmark's doing fantastic, and then you realize later you're not even testing your benchmark. So always be aware that this can optimize out, and this is just an easy way to make sure that it doesn't do that. Another thing you want to do is you don't want to benchmark setup. So a lot of times if you're benchmarking something, you need to do a bunch of setup. Maybe you need to create some test data. Maybe you need to connect to some external systems or spin up some internal systems to the actual application. And what you want to do is you want to kind of do all that expensive stuff up here ahead of time. And then right before you actually run your benchmark, you can do a b.reset timer. And this reset timer basically says all this stuff that was happening here, we don't want to count any of that time. And so you do your b.reset timer right before your loop. And when you do that, that will give you a much more accurate result for your actual test. So it's pretty important to understand any of your setup that's up in here. You're going to want to go ahead and run your b.reset timer right before your loop at that point. A lot of small benchmarks don't matter, but if you're doing more complicated benchmarks, this is a pretty big deal because it'll skew your results quite a bit. We do have an exercise here, which you're more than welcome to do. However, we probably aren't going to do that today. I will stick around for another 10 minutes. We got some extra time here left. So if you want to do this, I'll stick around and answer any questions. So feel free to do that. But we're not going to do it today. I actually do have the solution here as well. So if you're wondering how to make sure that actually works, here's the actual solution as well. And here's the actual output from that solution, at least when I got on mine when I ran it. So you should have some similar results for that. So that's kind of the end of the benchmarking and testing part right there. If you have any questions, let me know. I do have one final slide deck to finish up on, just to kind of finalize out the actual course today. So just for some additional support out there, if you're looking for some more docs, obviously all of the Go docs are really good. Most of you should be on the Gopher Slack. I see about 9 of you joined here, so that's really nice. I definitely encourage you to get out onto the actual Slack, because that is where a lot of Gophers hang out. The Go team's out there occasionally as well. Just a great place for resources. There's 20 or 30,000 people out there, so it's a huge resource. It's kind of the de facto if you're looking for help for Go. So definitely get out there. It's just a great place. I hang out there quite a bit. Feel free to mention me anytime if you have a question. I'll try to help out whatever I can. There's some really good books and videos out there, so I got some links in here. There's Just for Funk by Frances Campoy, and it's just a fantastic little small YouTube channel that he has out there, usually anywhere from 20 to 30 minutes on a lot of these. Just really, he does some great presentations. So I definitely recommend checking out the Just for Funk stuff. A lot of great videos out there, really good topical stuff. And then training for Gopher Guides. Obviously, we're doing some free workshops here and trying to help out the community. We obviously do paid training as well, virtual or in person. So if your company's looking to get a leg up, you got some big Go projects coming up, you need to do some training for some cross training for some teams, definitely think about us and ask us any questions. We'd love to come out and help your team. We do a lot of training for Fortune 500 companies all the time. So we're very versed in it, and we know what the companies need. So we'd definitely like to help you out. And finally, here's all my information. So if you need to get a hold of me for any reason, I'm on GitHub, I'm on Twitter, I'm on LinkedIn. Feel free to email me. If there's anything I can do to help you out, please let me know. So that's going to kind of wrap up the workshop today. We're coming in right about an hour, so that's fantastic. Again, if you have any questions, let me know. This will be on our YouTube channel when we're done. So if you don't have the YouTube channel, I'll post it again here in chat. Right there. That's the YouTube channel. And let me bring it here. So as you can see, that's our YouTube channel right there. We've got the Go Bootcamp out there too. So if you weren't part of the Go Bootcamp, feel free to go out and watch that one. We did that about a month ago. And so we went ahead and did that. We also have, let me bring up one more link here. So this was the testing and benchmarking. We do have another webinar coming up here in a couple of weeks, which is the Buffalo Bootcamp. So if you're interested in actual learning how to do rapid web development in Buffalo or Go, this is another great link right there. Feel free to come out and sign up for that one as well. That'll be run by Mark Bates, who is the actual creator of Go Buffalo. So again, thank you everybody for coming. If you have any questions, let me know. I'll be online for a while, or else hit me up in Slack anytime. I appreciate everybody coming and taking the workshop with me.